Well, thank you all. Thank you everybody for coming. This is a talk about Whippet, which is a garbage collector library, which I've been working on as a potential and hopeful replacement for the garbage collector library used in Guile. And in this talk, I have I have one big part, and one medium part, and one tiny part. And the big part is the big idea. I try to explain what's going on with this thing. And then we're going to look at a bit of what do we win effectively, like what changes in Guile and potentially other systems by switching to Whippet, and then some forward-looking statements. So starting off with a big idea, it's kind of like I said in the talk title, Whippet is a practical memory management upgrade. It's a memory manager, that's upgrade, for Guile and beyond. And we're going to break this down and kind of keep repeating it and looking into the individual parts. And so, first of all, it is a memory manager, meaning it is a garbage collector. It is something that takes care of allocating and reclaiming memory in your program. And ideally, it preserves a property that you never reference memory that's unused. You eliminate use after free bugs by using a garbage collected system. And it efficiently reclaims memory, so it keeps the system fast. But before we go in, I'd like to give a little bit of texture. You know, like when you go into a store and you want to touch something and see how it feels, you know? We're going to touch the API a little bit and see what it means to embed Whippet into our programs. So I just have like 3 slides here. This is a minimal get up and running with Whippet. It's a tiny C library that goes in your source tree. It's not something you dynamically link to. There's we're declaring our general, some parameters to this GC init function. But notably, I want to say that we declare a heap type, which is opaque to the user, and a mutator type. Every thread has a mutator. Every part of your program that allocates has a pointer on a mutator. And when you create a new thread, you create a new mutator from your heap. And there's a opaque set of options that effectively parses parameters for the GC from like a command line or an environment variable or something like this. And we can also collect statistics, have a set of callbacks that the garbage collector will invoke like when it starts a collection. So you can do histograms and things like this. So once you've called GC init, you've made your heap. You now have an initialized heap and mutator, and then you can allocate, and you allocate by passing in the mutator with the size. And of course it returns a void star because this is C. Let's look a little bit deeper, right? Options, for example. Here we can allocate some options and then set some values. In this case, we'll just set some things from the environment, right? This might allow you to control the parallelism of the mutator or the heap size, the growth policy. Are you going to have it fixed? Are you going to allow it to grow? Or do you dynamically increase it when your mutator is allocating more and then try to shrink the heap when it's reached a steady state? The embedder actually provides a definition of how do you enumerate the edges that point into the graph of live objects. So this struct GC mutator roots is actually provided by the embedder, meaning the Guile in this case, instead of Whippet. And it's Guile who attaches roots to a particular mutator. And then the collector will be able to trace those. We'll see that in a minute. And additionally, if you have a generational collector configuration, you need to have write barriers. Write barriers are tiny bits of code that run when you mutate a field in an object that help the garbage collector keep its internal accounting of, like, for example, if it's trying to partition objects into 2 sets and you mutate one of the edges, it might need to move an object into one set or into another set. Whippet is generally a cooperative safe point system, so the mutator will have to... every allocation is a potential garbage collection point, but if you go through a long period without allocating, you might need to emit a safe point. And all of these have like fast paths and slow paths, and the fast paths can be inline and such. And for some collectors, you might need to like pin an object. That's the general shape of the API. And then on the embedder side, which is typically not something users have to do so much, but it is for each embedding, you need to implement the kind of the hooks into how to trace the graph. essentially. So if you get an object, how do the embedder implements a GC trace object function, only one of them for the whole program, that needs to be able to trace any kind of object. So you need to be able to introspect somehow on this object, and that is up to the host. The garbage collector does not impose any restriction or requirement on the representation of objects as a purely embedder concern. And you call a visit function for each field, essentially, on it, passing some data, the usual thing. Same for how do you trace and mutate roots. And this leaves it completely up to the embedder as to whether you have handles, stack maps, what your strategy is for tracking roots and making it possible for the collector to enumerate all the edges into the graph. That's all the code that I'm actually going to show in this presentation. So it is a memory manager, has this general feel. It slots into your source tree, and I'm designing it with a particular use case in mind, which is Guile. Guile's very old. It's like, 30, 32, could be 40 years old, depending on how you count it. And it has a garbage collector that is the Boehm-Demers-Weiser garbage collector, a conservative garbage collector. Works very well, but it's old, and there are better things to do now. And there are things we would like that the Boehm collector does not give us. We would like to be able to do allocation like bump pointer allocation instead of free list allocation. We would like to have some features that are impossible to implement in the Boehm collector, like ephemerons. We would like to have heap growth and shrinking. We would like to have more control over the overall size of the heap, a bit more visibility into the dynamics of a program and an embedder and a heap usage, to be able to control things a bit better. We would also like to be able to experiment with different collector algorithms, actually. There are a few different algorithms out there and a few different ways you can compose spaces. And it's not always, there's no global optimum here. And so it may be that an embedder needs to choose a particular allocator for a particular workload, and that's how it should be. In Whippet, this choice is done at compile time, because we want compile time specialization of the collector to the embedder and of the embedder to the particular collector configuration. It's not a dynamic thing like in Java. That would essentially require JIT compilation for good performance and have more warm-up and such. This is a different point in the design space. And so as something for Guile, we would like all of these things, but we have to be able to get there from where we are, right? And where we are is a funny place. Like we still have a fair amount of C code. We still have a lot of, effectively, we don't explicitly add each root, each reference from a local variable that points to a garbage collected object. We don't put them anywhere. They're just on the stack, and we rely on the Boehm collector to essentially look at each word on the stack and see if it might point to an object. We actually support this use case in an effort to provide a path from where we are to where we would like to be. And we're going to be evaluating whether this is a useful strategy to keep or whether we should move off to what's called precise routing, which is a possibility, but we can talk a little bit about that later. So the idea is that Whippet is like a load-bearing abstraction, but because it's the load-bearing part of this abstraction is the API, and the fact that it's supported by this load-bearing point allows us to pivot, right? So if in Guile we switch to Whippet, we can start with behavior that's very close to what the current collector does, and over time we can change things to enable different configurations and more performance. So the first collector that we're going to try in Guile after the Boehm collector that I would like to try is this MMC collector, because it supports conservative roots from the stack and conservative roots from global heap sections, and optionally even conservative edges between objects. And so in the Whippet library, there are a few collectors. Collectors are configurations of spaces. There are three main collectors, like three main collector variants. One of them is the MMC collector, the mostly marking collector. It mostly marks objects. Sometimes it can copy and evacuate objects. So that's where the name comes from. And it's composed of two spaces. the space we call the Knoffel space and the large object space, or the low space. And in the Knoffel space, this is the one that if you were here a couple of years ago when I presented first about Whippet, I was very excited about, because this IMIX design allows for improved performance in bump pointer allocation and optional allocation and optional conservative roots. And I was just so excited and made this prototype. And at that time, Whippet was essentially just this space, right? And in these interceding 2 years, Whippet has become more of a collector, right? Or family of particular collectors, but like an embeddable library. That's the essential difference relative to a couple of years ago, besides performance and bugs and features and stuff. Like we've gone really from prototype to something that is pretty much ready right now. And the Knoffel space has some memory overhead, not 12%, because it records a byte per granule, yes, and a granule is 16 bytes. Is it 12% or 6%? I think it's 6%, isn't it? That's how it is, actually. No. No, yeah, right. It's 6%. It supports pinning, which is and pinning permanently, maybe because you really need this object not to move. You don't know. You can't be sure that the references to it will allow moving for whatever reason. And it can also pin roots to prevent them moving. The roots that come in from conservative roots, the ones you might not know that actually refer to an object or not, those objects can't move because we're not sure if the edge coming in is relocatable or not. But then if you can precisely trape the intra-heap edges, then you can move everything else, which is a pretty interesting possibility. And it's also optionally generational, using what's called a sticky mark algorithm. And then larger objects are never moved. They're allocated with mmap effectively. And when they get freed, they go on a free list that after a couple seconds, if that free list entry hasn't been reused, it gets returned to the OS. So we try to minimize virtual memory traffic here. And it's optionally generational as well. That's probably the space that's going to be the main one for Guile, but we'll see. So, and Whippet is an upgrade, I think, not just for Guile itself, but also potentially for other systems. So I'm building it with Guile in mind, but I also want to target other small languages, which is, I think, some folks in here. That when you build a system, you've got a lot to build. Right? You have the compiler, and you want to build a GC. You want to build everything, right? I'm speaking from projection, right? But you don't want to have so much time, and so it would be nice to be able to just include something that works and that stretches farther to the state of the art than something like the Boehm collector. And I think we're going to be able to do this. Especially in new systems often have precise roots. And so one of the possibilities that Whippet gives you is a fully copying collector or a fully moving collector. So this is another new one relative to a couple of years ago. This is a parallel copying collector. It's a large object space, or managed just as before. And then the copy space is a block structured space. It's stop the world, but highly parallel and highly parallel for mutators as well. When a mutator needs to allocate some more memory, it does bump pointer allocation in, I think they're 128 kilobyte blocks. When it runs out, it gets a new one. It's all lock-free, so it scales very well to, and it's always compacting, and of course it has 100% overhead because it's a copying collector, right? When you copy, you need to reserve all that space. We also have a generational configuration here. So instead of having a copy space and a large object space, we have a copy space and a copy space and a large object space. But because it's generational, you can limit the size of the nursery, and you can limit it ahead of time. And so you can do a number of tricks to make it cheap to test whether an object is in the nursery or the old generation. This needs to be tuned. It's a relatively recent thing, and tuning generational GCs is very tricky. But what it does have is and this is the same thing for the generational configuration of the mostly marking collector. It has a very precise write barrier, so it precisely records fields that point into the new generation. It's not a barrier that marks like any object within this block, for example. It's really precise fields. Field logging right barrier is what it's called. Yep, very good. In this collector, objects stay around in the nursery for one cycle, and then they get promoted up if they survive. And then finally, this is the third major collector that is in Whippet, is the Whippet API, but with the Boehm collector behind it, right? And this mostly works, though, it works, but it has a difference relative to other collector configurations in that it's not cooperative. If you're familiar with the Boehm collector, it's an amazing hack, but it stops the world by sending signals to processes. So you can be stopped anywhere. Your embedder has to be a little bit more ready with regards to being able to trace its roots at any point. But the other nice thing with the Boehm collector is you don't necessarily need to implement GC trace object there, because we don't actually call that. We allow the Boehm collector to conservatively track all edges there. Right. All right. Practical memory management upgrade for Guile and beyond. So practical on that side, I say it's for embedding, and I say it's not just for Guile. And this is another new thing. How do you test this? Right? I wanted to have these properties that it's embed-only. It's not something you link to. You include it in your source tree. And it has no dependencies. It's C for better and for worse. I think we all know the advantages and the tradebacks there. And it's something you can hack on. And the thing I've been working on to test this, I know some of you know. The other ones, you're going to find it funny. It's another scheme implementation. I wrote a special scheme implementation. It's not a great one. It just compiles to C. And the whole purpose is to test Whippet in its different configurations. Because writing, when you have a garbage collector like this, you don't actually want to write, the embedder shouldn't really have C programs. It should be a language implementation. And its compiler and runtime should ensure the property that like you enumerate all the roots, like handles all your stack mapping and stuff. And what I had before was like manually written C programs that were the micro benchmarks, and WIFL allows me to write scheme programs that are the benchmarks. Still micro benchmarks. It's kind of where we are, but and I also wanted to test like explicit handle registration versus stack maps and things like this. His motivation was testing, and like I say, it's caught many bugs. So for Guile itself, here's the plan as I presented to Ludo. Right? The plan is first switch Guile to use the Whippet API. Right? Everywhere you would call the Boehm collector, instead call the Whippet API and thread the mutator through everywhere that you need, like this sort of thing. But use the Boehm collector behind it, so we're not actually changing behavior. And then let's switch over to the mostly marking collector with conservative roots. Maybe even conservatively tracing the heap. We'll see. Ideally, you would want to implement GC trace objects so that we get compaction and all these benefits. And then potentially add support for generational collection. We'll see what this buys us in a bit, but it requires write barriers. So we have to be careful about this. Existing Guile users don't have these write barriers in their code. So there's some aspects here. And then maybe we can switch to mostly marking the novel space in the old generation, and then a copying nursery, which would be a very conventional and more or less state-of-the-art configuration. And I should mention here, I've been working on this over the past few months, along with Sprightly work. And my work on Whippet has been sponsored by NLNet, so I appreciate that very much. Thank you. There's more. But yeah, great. All right. So, and it's for Guile and beyond. I have a few more things I want to do, like WebAssembly to C, but like WebAssembly with GC, and you embed this as as a garbage collector, so that way we can run actually standalone programs compiled from Scheme to WebAssembly. And I'm also targeting OCaml and R and things like that. Right. So what do we get? Right. I don't know if it's top line or bottom line. I'm not sure how people do accounting, but what we can expect more or less is for a given memory size, we can improve throughput. Could be 20%, maybe maximum 40. Sometimes it's actually quite a lot, and sometimes it's littler, but that's a general range. And then also we can end up with systems that use less memory, right? That at a given throughput you can use less memory. So let's see. It's going to be a bunch of graphs. We're going to go through them faster than is recommended, but here we go. All these graphs are space-time graphs, right? This is how you evaluate a GC, because a GC is a fundamental space-time trade-off. The more heap you give it, the less time it takes, essentially. And so you expect to see a curve like this. This is a heap size multiplier on the x-axis. As you get towards like a one times live variable size, then you're going to be collecting all the time because you have very little space to work in. And as you have more space, then the collector can do better. The green line is the mostly marking collector on this one particular benchmark. It's Boyer standard Gabriel benchmark. The blue is the Boehm collector, and then the orange is the parallel copying collector. And they're all a bit compressed here because we see a couple things. One, the mostly marking collector allows us to access these smaller heap sizes that we cannot get in the other collectors. Right? Nobody else, they all fail at this size. This is setting a fixed heap size. Two, we do better than the Boehm collector at every point here. And the Boehm collector is the blue line. Lower is better. And then if you switch to another garbage collection algorithm, like a copying collector, which has different performance characteristics, it beats the mostly marking collector at larger heap sizes, which is what we expect. So if you have a workload like you need maximum throughput and you have a lot of memory, then you might want to configure your collector to use the parallel copying collector, for example. And we see similar things in like this other test here. This is a partial evaluator test. Again, mostly marking collector is doing pretty good. Looks like we actually cross here with the Boehm collector, it seems. All those tests before were with one mutator. If you have 8, this is on my laptop with 8 cores, 16 threads. If you have 8 threads, then you see a similar graph, and we have a pretty good advantage here. It's between 4 and 6 seconds here for the Boehm collector versus MC. There in the sort of tail of that graph, and similar things for p-eval. Right. You might want to ask some questions, right? Because there's a lot of narratives about garbage collection about what is actually good. People make statements and you don't know if it's marketing or not. And so that's another one of the goals of Whippet is to be able to use the same system but different configurations and see how do things perform. Like I have found 2 things. One, conservative root finding is quite fine, right? It's not actually a problem in these micro benchmarks. And 2, generational GC is very complicated. It can decrease throughput in my current tunings, which might not be optimal. They certainly reduce pause times, which I'm not going to show. But those are 2 things. Okay, so this is first 3 different configurations for the mostly marking collector on this one micro benchmark. That's, I think, if it's 8 mutators, this one's probably about a gigabyte heap or something like that. As you can see, all 3 mostly follow the same shape. The blue here on the top, the dark blue, is a configuration in which all edges are conservative. The lighter blue is a configuration in which edges into the graph from the stack are conservative, but edges within the heap graph are traced precisely. And then the red here on the bottom is the precise one. There's almost no difference between the stack conservative versus stack precise configurations. And there is a difference between the fully conservative. It's less good. It's not a huge difference, right? So it is something that you can accept. If engineering-wise, that's a configuration you need. Same graph, different test. Generational collectors. We're not winning. We're not winning currently. Here is my whole heap collector, and for some reason, my generational configuration of the mostly marking collector is not as good in terms of throughput. This can be a possible result, but it's a little bit perplexing in some ways. So there's still some investigation to do here. And I have a similar difference for the generational copying collector, which has different characteristics because the mostly marking collector, the nursery is the entire heap size, versus for the copying collector, the nursery is just 2 megabytes per active mutator. So there's more investigation to do here. It's a little bit... I don't fully understand these things, but the conclusion I'm taking is that generational GC is a little bit complicated to tune, which is, I think, mostly well known. Finally, future. Finally going to slam it into Guile. I think it's about this month or so that I'm going to start hacking on that. Maybe if y'all got a language runtime, we should talk, right? We should see how we're doing. Eventually, I would like to do concurrent marking so that you have the tiny pause times, sub-millisecond for the minor GCs. And then when it comes time for the major GC, you've already marked most of the graph concurrently. And so you can minimize that pause time. And then there are other things I would like to investigate. This garbage collection algorithm called Elixir that uses some reference counting for the old generation for prompt reclamation of the old generation code. Yeah, that's it. So there we are. Try it out. Ask some questions. Boy, we went straight into that, didn't we? Thanks for coming along. Any questions? Say what? What pointers? Colored pointers. What is a colored pointer?
Basically, we're using a couple of bits of the pointers.
Yeah. We are not planning to use colored pointers because I don't want to impose that kind of requirement on the collector. On the embedder. It's an interesting possibility, but it's not within scope. Yeah. Another one, Dave?
Yeah, sure. I know you didn't focus on it in this talk, but I'm interested in graphs about time, because I'm interested in how Whippet performs for some real-time applications, video games, that sort of thing.
See me later today.
Okay.
Yeah.
All right, everyone, please squeeze in. We're going to have a full house.
In the middle, is there a question? No. All right. If you're writing in Rust, you should use MMTK instead of Whippet. And if you're writing in Zig, I don't know what facilities exist for this sort of C source code. It's really not appropriate, I would say. Yeah. Sorry, the question is whether Rust and Zig should use Whippet, and the answer is no. In Rust specifically, MMTK is a good option, and in Zig,